Welcome to Breadboarding. This is video 52 in the Breadboard 8088 PC series, and this is part 7 of the CGA video controller. So in the series, we initially developed a NanoComp 8088, which basically just had the 8088 processor with an LED display and keypad and a monitor program. And then we extended this to become a basic floppy disk PC. So we developed a monochrome display adapter video controller, and we're able to get it booting MS-DOS 330 off of floppy disk. And this final stage, what we're looking to do is to build out a PC capable running early versions of Windows. So we've already built the IDE disk controller and got the BIOS to boot MS-DOS from hard disk. And this main step we've got left now is the CGA video controller, which is compatible with early versions of Windows. In the last video, we were trying to get the video output to actually look like this pattern, which is basically just the 16 CGA colours, but we weren't quite getting all the colours coming out properly. Now I did a bit of tweaking to the test program, and I also added some decoupling capacitors to the power supply lines, which I'd forgotten to put in, and it did improve a little. However, there's still a little bit of variability. Sometimes when you repeat the test, it comes up with different colours, but this is actually what the colours look like now. So apart from the right hand side here, where you can see there's the delay that we need to introduce for horizontal sync and vertical sync to actually shift things across, you can see that in fact if you toggle between the two, then the colours are pretty reasonable. So for the moment, I'm going to hold off investigating this further until such time as they've added all of the data bus buffering and things like that. So in this video, what I'm going to do, this is where we got to last time with the CRTC IO port decoder, the dot clock, a 25 megahertz VGA dot clock, the PLD for doing the various timing signals, and the digital analog converter, which produces the signals to send out to the VGA connector. And what we're going to be doing in this video is adding the character generator ROM and also the shift register that then takes the various raster image rows from the character generator and serializes those. And all we're going to do initially is get the 1-bit output of here to toggle between the foreground and background colors in the video DAC. And what we'll do is just change the 0 value will be black as it was previously, but the 1 value will just change that to be bright white foreground. So if you have a look at the KiCad schematic, you can see that this is the character generator ROM. This is the shift register that takes the data outputs from the character generator ROM. This has the individual raster lines making up each character. And you can see here that the CRTC provides the raster address lines which go from 0 to 3, but we're ignoring RA0 in this so that we double scan each line. Because the original CGA was only made up of 200 rows across the screen, but in fact with VGA we're going to be doing 400. So by ignoring the RA0, what this does is doubles each line. So we go from 200 rows to 400 rows. Once we've hooked up the output here to the shift register, the ATSR latch, so the attribute shift register latch, when that goes low, it takes all of the outputs of the character generator, loads it into the shift register, and then as the clock then rotates each of those, we actually get the output coming from S-dots here, and the S-dots output, once we've done the PLDs for the video output stage, we'll actually then output things to the video DAC here. But to start with, all we're going to do is to take the output from here and just feed it into the P0 line here, and that will just toggle between the black background and the white foreground. So what it should allow us to do is to produce something that looks a bit like this. So this is a screenshot from the original NanoComp video controller, and all this is showing is what happens is when we take the CRTC address lines and we feed those into the character generator ROM. So rather than taking the character generator ROM values from 0 to 255 from the video RAM, all we're doing is just feeding the CRTC address lines into here. So this will basically rotate us through 0 up to 255, and then will just take us all the way around again. So you can see here, just gives us an indication of the test pattern. Now this is in fact VGA, and this is actually VGA of 480 lines down the screen here, because this in fact the characters are made up of 16 lines and there's actually 30 lots of 16 here, so this is 480. So we expect the CGA characters to look a little different from this, but we should get a similar pattern. So if we take a look at the different fonts that we can use here, so this is the comparing the CGA standard font, which is a slightly wider, thicker one, the thin CGA font, and the original MDA and VGA font as well. So the CGA default font is for 640 by 200 resolution. The vertical lines here will actually be 2 pixels wide, and they are an 8 by 8 cell. If we then go on to the thin version, then in fact each of the vertical lines is only 1 pixel wide, and I'll show you this in a minute using the Frapped font editor. But if we toggle between the two here, you can see that the default one, which is the thicker one, is a little bit wider, and that was, I think, so that it would actually work on composite monitors and things like that a bit better than it would otherwise. And then this is the monochrome display adapter font, so these were 9 by 14 pixels. The VGA fonts we actually used in our monochrome display adapter, so this would actually do the full 640 by 400, and we had 25 rows of characters of 16 pixels. So this is what we did in the previous video adapter. So where we get these fonts from Traption is the utility we use for actually looking at these fonts, and the VGA fonts are available from int10h, the website there, so int10h.org, which is all about video and fonts. So we can download the zip file there, expand it, and then all the fonts are in there. So we're looking at the VGA 8-bit wide fonts, which are 16 high, and the CGA 8-bit fonts, which are 8 rows high. The default one has thick characters and the alternative one has thin characters. So you can see here, this are the thick characters, so each of the vertical lines has got 2 pixels, and I think there's another slide here, there we go. We've actually got the thin font loaded there, and you can see the vertical lines only have 1 pixel. So this is running in DOSBox. So we're just going to load the default CGA font. This is CGA F08, which means it's made up of 8 lines. And you can see there that the vertical strokes are actually 2 pixels wide. Then on the other side here, we're going to load the CGA thin F08, and you can see here that the vertical characters here are only 1 pixel wide. So if we actually switch between 1 and 2, you can see the difference in the characters. They'll just load in the VGA fonts. You can see here this is VGA F16, so this means it's made up of 16 rows. So we will also put the VGA fonts in the top area of the EEPROM, so that'll allow us, if we want to switch over to this font if we wanted to. Now in fact, the Compact Desk Pro video adapter, although it's producing CGA compatible graphics output, then in fact in text mode it actually, I think, used these larger characters. So we might try and do that at a later stage to see if we can make the video output in text mode look a bit better than the default CGA. So what we're going to do first of all is just to burn these fonts into the EEPROM. So here is the EEPROM. It's not wired up, there's no power, and then here is the shift register. We're just going to need to wire in the address lines here over to the CRTC address line outputs just to provide our 0 to 255 cycling. The data lines here are going to go from here and to here, and then the output, the serial output here, is just going to go over to the P0 input of the digital analog converter over here, so that we can toggle between foreground and background colors. So just going to pull this EEPROM out, and we'll put it into the EEPROM programmer. You can see that's now in the EEPROM programmer. So what we're going to do now is to go into XG Pro. This is a utility that allows us to program EEPROMs. So it's always a good idea to read the current chip just to make sure you've got it inserted correctly. So you can see this is all FFFFF. Now in fact what we want to do, we're going to be looking at this font, CGA F08. We're then going to take the thin version of that as well. And then also at the top 4K, we're going to put the VGA one. So you can see that we've got two 2 kilobyte CGA fonts and one 4KB font. So that's going to mean we're going to fill the whole 8K EEPROM. So what we need to do when we load these, we need to make sure that for the second and third font that we don't overwrite what's already here. So you can see here this will clear the buffer when loading the file, but for the second and third ones we don't want to clear the buffer, and we're also going to want to put an offset in here so that it loads it in the correct area. So if we browse for the fonts, we're going to choose the default thick one to start with. So that's CGA F08. If we load that in, we can see as we scroll down that when we get to 800, then that's the end of the font. So the offset we need to use for the next CGA font is 800, and we need to make sure we don't clear the buffer. So I'll just disable that, and we'll put 800 in there, and then we just need to choose the other font. This is a thin font. Okay, so that's loaded that in. That should go down to 100. There we go. So you can see that at 100, which is about 4K, then we've got space there for our VGA font. So we'll just load in the VGA font. Again, disable that. We'll put 1000 as the offset, and then we'll choose the VGA F16 font there. Okay, so that font now goes all the way to 1FFFF. All we need to do now is to program that. Okay, so we've programmed our character generator. So now all we need to do is to wire this up. So what I'm going to do is to wire that up, I'll speed it up and commentate over it. Then once we've done that, we'll just need to modify our test program so that the background and foreground colors are black for the background and white for the foreground. And then we can just make sure the output of our shift register is toggling between the foreground and background, and then we should be able to see a test pattern. So just need to take the character generator EEPROM out and seat that. Leave enough space around it. So now we've got a number of wires that need to go in for the power and tying certain inputs to ground and to 5 volts, including some of the address lines so we can choose between our different font sets. So just putting in the power rail for the character generator on there, which has just got to go around the power connector. Just move the decoupling capacitor down a bit, shovel some of the wires away so we can get the tie to ground in there. Then do the power rails for the shift register down there. Can move one of the pull-up resistors out of the way. This is a downside to building things out in stages like this. It does get a bit messy. If we were to do it all in one go, we could just put all the power lines in one go. Now we need to tie some of the control signals to ground, so the clock inhibit and this other one we need to tie to ground, and then the clear, for the moment we're just going to tie to 5 volts. That will go to the output from one of the PLDs to do clear on reset and on display enable going blank. So now we need to wire up various control lines and the data and the address line. So the ATSR latch and the dot clock are going to go in here, and then we're also going to have the output go to the DAC and do the data lines. So just to move some of the cables out of the way for the moment whilst we're doing this, and there was a serial cable for the USB that we need to get out of the way there. So now it's a bit clearer. We're now going to put in the dot clock first. That comes out of the PLD. So that dot clock is generally going to be 25 megahertz, but in 40 character mode it will be half that frequency. That's the latch signal that loads the data from the ROM into the shift register. And now we're just going to feed in the various data lines. So we're going to be doing the D2, D1, D0 at the top there. then the D3, D4, D5, D6 and D7. Something like this is not worthwhile using ribbon cables because it's a bit scattered around the place. Okay, and then we now just need to just check that, the zoom in. Now we're going to take the outputs that are currently plugged into the video DAC and put one into the output, the shift register, and all the others are now tied to ground, they're all 0. Now we need to take the raster address lines and feed those into the A0, A1, A2 address lines for the character generator, so that allows us to do 8 rows per character. If we want to do VGA, we'd actually need 4 address lines for 16 rows per character. Okay, and now we need to wire up the outputs from the CRTC addresses, and we're going to wire in 5 on the one side and 3 on the other. You can see how fiddly it is to do DuPont cables when they've got individual connectors rather than in the shells, when I replace these with shells. But since this is a temporary test, it's not really worth replacing the connectors here with the shells. So putting 5 at the top there for the first 5 addresses, and then we need to do the other 3 addresses there, and again you can see they're sort of not side by side, they're sort of A8, A9, then a gap for A10, and then the A11 and A12 are used to determine which block of font we're using. So we've checked off all those wiring, all of those things up there, and our S-dots output goes there. Okay, so we've now wired up all of this. So we've got the address lines coming from CRTC to provide the character addresses, just so that we'll cycle through all 256 characters. The raster address lines are going up to the lower first 3 address lines over here. We've got the output of the shift register is going to bit 0 of the digital analog converter there, and the other lines are actually just tied to ground, so they're all 0. And if we have a look at the test program, so CGA test 3, this is based on test 1, but we've relocated it to a bit lower in the memory to 6000 segment, and palette 1 has been changed from blue to white just so we get a better representation when we switch between 0 and 1 on the palette. And down the bottom here you can see that 0 is black, 1 is now white. I'll be commented out the blue. All the other colours would be the same, but we're only going to be switching between 0 and 1. So that looks like it should be okay. So we're just going to assemble that. That's assembled. Going to power on the breadboard PC and then download this, and then we'll see what we get coming out of the video. So just send the program down and then we'll run it. So that has run. Okay, so let's just have a look at the VGA capture, see what is coming out of there. And great, that does look like we've got our character set. So you can actually see it's just the wide character set repeating again and again and again. Now if we just try changing one of the links on the character generator, they will change it from being grounded to change it to 5 volts. So you should see that's now the thin character set. And if we now switch it back to grounding that pin, we should see it go to the thick one. So that's the thick, that's the thin. Now in fact, this will not work properly yet because we're only doing 8 address lines. But if we were to change the A12 line that switches between the VGA font and the CGA font, we're only actually getting half of the characters. So you can see there that we're only really getting the top half of the characters because we're only actually scanning 8 out of the 16 lines. So if we wanted to, we could obviously swap things around and add in all 16 raster address lines, and we'd actually be able to get better CGA characters. But for the moment I'm just going to put it back to our wide fonts, and I think the thin ones perhaps look a little bit better. So we're going to switch this to use the thin ones for now. Okay, so we've got our CGA character generator coming out, so that means the shift register and the fonts are okay. We need to now start to hook up all of the video PLDs. So if we go back to the block diagram, so we've completed wiring in the character generator, shift register here. Now the next step we need to do in the next video, we're going to be adding the blink PLD that takes the vertical sync, then divides it down to provide the cursor blink and the character blink clocks. It also does a little bit of processing on the horizontal sync and vertical sync signals. We've also got the attribute latch PLD, which takes the data from the video RAM when we add it and then selects between the foreground and background colors. And then there's two other multiplexers and video output logic that actually handles all the video rules to do with handling the various graphics color modes and to handle blinking characters, foreground, background, all that sort of stuff. So we're going to need to do that in the next video. But for the moment, I'm going to end the video here. So if you don't want to miss out on future videos, then please hit subscribe. And if you found the content interesting, please hit like. It just helps to make the videos available to a wider number of people. Thanks for watching.